Okay, this is covering the lesson on simple harmonic motion. And I'll start off with the definition of simple harmonic oscillation. It's an oscillation that's a back and forth kind of a motion that follows a sine wave or cosine wave position with respect to time. So we generally put it into a form that involves the cosine, although we could do it just as easily with a sine, but just by convention, there's the cosine. So let me draw the basic cosine function. Let's see, and we don't have any colored chalk, so I'm going to draw back there. Outline. All right, so cosine, this is the abbreviation that we generally use with it. It's SHM for simple harmonic motion, or SHO for simple harmonic oscillator. A cosine, and by the way, I'll use the abbreviation FCT for function. I've got a few other shorthands that I'll introduce to you that keep me from having to write things out too far. So if we have here y versus x, the cosine ranges from 1 to -1, like that. It starts at the origin at +1, goes down to -1 and back up. And x, actually, sorry, I should put here, instead of x, let me do this in terms of theta. Now, there's a reason for this. Theta, in fact, the Greek letters in general, we tend to use those to refer to angles, which involve circular motion. Well, this isn't yet, obviously, anything to do with circular motion. But in a couple of sections, I'm going to connect it to rotational motion. And so I'm going to go and have the angle measure there. All right, so I've got y versus theta, and when we get all the way up to 2 pi, now theta is going to be measured in radians, which is a dimensionless number. When we get all the way up to 2 pi, it's back to the value where it started. So 0, let's see, this is going to be pi over 2. That's 90 degrees. This is going to be pi, that's 180 degrees. This is going to be 3 pi over 2, 270 degrees, and then 2 pi, which is 360 all the way around. And then the cycle, of course, repeats. By the way, the cosine function is completely symmetrical around the theta equals 0 point. So it continues on to negative angles the same way. So negative pi over 2, negative pi is the same as at pi, and so on like that. This is what we call a symmetrical function, which is also called an even function. Meaning if you put in some value into the function, so here y equals the cosine of theta. If you put in, say, pi for theta, the function gets you out -1. If you put in negative pi, you get out exactly the same value, -1. So it doesn't matter whether you put in theta or negative theta, you get the same thing out. That's an even function. The sine, on the other hand, is an odd function. The sine starts off at 0 and goes up from there, but on the negative side, it goes down from there. So it is anti-symmetrical. If you put in negative theta instead of theta, you get out negative times the sine of theta. But we don't need to worry about that right now. Okay. In particular, for a simple harmonic oscillator, we're going to have make sure you use radians on your calculator when you're putting in numbers here. in degrees for this when we're doing the calculations, well, if you put in degrees into the cosine, that's fine, but we're going to put in functions for theta. And the functions are never giving us things in degrees. They're always going to be dimensionless numbers, which means radians. Okay, so when I put in here, in terms of what this is just a basic cosine, but if I put it in terms of what a simple harmonic oscillator will have, it's going to have slightly different scaling here. So for a simple harmonic oscillator, I can use my abbreviation now, SHO. I'm going to have something that swings back and forth with respect to time, motion over time. So I've got position, which I'll give x, and I'm going to have time, which will be t. Aren't we used to putting x on the horizontal coordinate? But in this case, it's not y versus x, it's position versus time. Now, otherwise, it's going to look the same. And of course, it goes on back that way too. Now, here, let's make sure that I've got a little bit of room. I'm going to have the maximum value for position be called A, and on the lower end, it's going to be negative A. A stands for amplitude. So the distance from zero, from the center of the position, out to the extreme end is called the amplitude. And it's the same distance as down here. So it's not all the way from one swing end to the other, it's half that distance. So it's from the center out. All right, and let's see, we've got 0 there. Now for the time it takes for a simple harmonic oscillator to go from its starting point all the way over and back to the starting point is called the period. And we're going to use a capital T to represent the period. Now the T stands for time. We've already got a T for time. We'll keep the time lowercase, and we'll have the period always be capital. So now we can scale the time coordinate in terms of fractions or multiples of the period. We start off at 0. Here we're at, let's see here, 1, 2, 3, 4. We'll take quarters of the period. So we've got the period over 4, period over 2, 3/4 of the period, and the whole period. Notice how that scales on with how we had it marked off in radians before, with 2 pi being a complete circle and a complete period there. And notice also then, you can measure the time of the period just from going from one wave crest to the next. You could do it from one, this is called the trough of a wave. You could measure from here to here as well. You could not do it from here, crossing the 0 line going down, to here, crossing the 0 line going up. You see it's going down this way and then back up. That's only half a period. You'd have to go from it going down here to it going down, crossing the 0 line again. Easiest just to do it from crest to crest. Okay. Now in this case, the function that we're plotting involves the cosine, but it's not as simple as just cosine of theta. Here, position as a function of time, x of t, we'll call that, is equal to the amplitude A times the cosine of 2 pi t over capital T. Now, if I just say t without saying capital or lowercase, assume lowercase. And I'll say capital explicitly. All right. That's the function that we've just plotted. All right, t is the period, and we're also going to want, let's see, t equals the period of oscillation. It's going to be measured in seconds, for example. Could be measured in minutes, hours, days, years, whatever, but the normal metric system is going to use seconds. Then we're going to have the frequency f, which will be defined as, so a triple equal sign, 1 over the period. I'm going to box that in because that's an important equation. And it will be measured in hertz. That's capital H, lowercase z, named for Heinrich Hertz, who had done early work with radio. The hertz, as a unit, is defined as 1 cycle per second, or just 1 over seconds. Inverse seconds, you could say. Now, notice I didn't write the word cycle over here. You know, 1 period, 1 completion of a swing per second. Because the cycle is not a unit. It's just it's counting. Whenever we're counting things, those aren't units. So a cycle per second, I can just say cycle and not have to write it up there. All right, you're probably familiar with hertz from radio frequencies, where AM radio stations are in hundreds of kilohertz, thousands of hertz, hundreds of thousands of hertz, therefore, and FM stations are in megahertz, millions of hertz. Okay, let's see here. We can write this out in 3 different useful ways. I'm going to erase this here for now to give myself a little space. All right, the function that we're plotting. One way of writing it is the way I first put it up there. Now, this is in terms of the period. A cosine of 2 pi t, it's time, over the period. And I can rewrite that, though, in terms of the frequency, where frequency is 1 over the period. Now, if frequency, f, is 1 over t, capital T, then I put that in here, and I've got 2 pi f t. 2 pi f frequency times lowercase t, the time. All right, so if you have something and you know its frequency, you can use this one. Or we can use what's called the angular frequency, which is omega. And omega is defined as 2 pi f. Okay, now angular frequency involves rotational motion, spinning, things like that, and we'll make the connection in the next section, how that ties in here. This, of course, is a very compact way of doing it because we can avoid that 2 pi floating around by itself. The 2 pi exists because one complete cycle of its cosine or sine wave takes 2 pi radians, comes with 2 pi radians. Omega, this is not a W, by the way. It's the lowercase omega. Notice it will always have that bit of a loop in the middle there, and it's a lowercase letter. Capital omega you might be a little more familiar with there. And you can see that they're sort of connected where these are just the little serifs there and there, and then this is they kind of made it a script loop in the middle. This used to be the kind of engraved form in ancient Greek, and this was the handwritten form. In the modern times, this became capital and that became lowercase. All right. And again, we use Greek letters when we're dealing with angular kinds of quantities, so angular frequency. All right. That means, by the way, if I substitute in f here, that omega is also equal to 2 pi divided by capital T. Therefore, the triangle of dots, omega is 2 pi over capital T. So, I want you to know that all three of these are ways of expressing the same function over here. But it's just different ways of putting in what the period is, or the frequency, or the angular frequency. By the way, if I say frequency, I will always mean f. If I mean omega, I will always say angular frequency. And angular frequency has units of radians per second. It's still then expressed, since a radian is one of those strange dimensionless kinds of units. Conceptually, I know that's always a bit tricky. But the radian says it's got that 2 pi is sort of implicitly inside of there, but we don't have to write radians on there. So it's still expressed in hertz, or 1/2. But we often do write the word radian on it just so we can keep straight what's going on and avoid driving ourselves crazy with the confusion. Okay, now I want to get it in terms of, we've got position as a function of time, we can get the velocity. Let's see if I